Hello everyone, here's another Alberta Physics 30 Diploma released item question review. This one's multiple choice question 27. It's a photoelectric effect scenario. We're asked to consider electromagnetic radiation of a constant wavelength being incident on a metal cathode from a photoelectric effect experiment. It says that the photoelectric effect is observed, which would imply that electrons are being ejected from the metal cathode. We're then asked which of the following graphs represents the relationship between the maximum kinetic energy of the emitted photoelectrons and the intensity of the incident radiation. Okay, so we'll just spend a little bit of a few moments just talking about this idea of intensity. Oops, I probably should do that red. There we go. Intensity, it's not, that word isn't really used anymore in our diploma because there's a little bit more meaning to it. For our purposes, we're going to just think about it as the number of photons, but we should know that it's really a product of how much power there is in the light, or the EMR, spread out over a certain area. So there's probably just two equations that are worth looking at just really quickly. We won't have to consider them in Physics 30 too much, but it's worth thinking about them. It's essentially, intensity is power divided by an area. So we could think about the flat surface, which is what would be the case here with our photoelectric effect experiment, which is then really simply just power over a surface area, or watts divided by meters squared. If, however, it was a point source in 3D space, which most light sources actually are, then we would be bringing in sort of this inverse square law, and we would have this 4 pi value in there to take account of the three-dimensional space. But either way, we're not going to spend any time on that. For all our intents and purposes for Physics 30, we're going to kind of ignore this and just consider intensity to be basically proportional to the number of photons. Okay, so it's just a count of the number of photons. Okay, so let's look at a photoelectric effect experiment here, or at least a simulated one. Hopefully you're familiar with this kind of setup. Here we've got our light source coming in towards our photocathode. In this case, it's sodium. And this vacuum is surrounding the photoelectric apparatus. And of course, we've got these wires that then complete a circuit. So very famously, Einstein showed that in this experiment, if the energy of these photons coming in is high enough, it will eject an electron from the sodium, and that electron will go in every different direction, but some of them will hit this plate over here and complete a circuit, and we should be able to measure that circuit. Furthermore, if we increase a voltage, if we change the voltage of our circuit, we can either stop those electrons or we can encourage them. We can play around with this voltage to either encourage the electrons to come across the gap or slow them down and stop them, and we can talk about energy equations from that point. We're not going to be interested in that particularly for now. We're just interested in what happens when we change the wavelength, which we can do by changing the color, and when we change the intensity. Now in this simulation it's called photon density, but really this is just, once again, it's just the number of photons hitting this sodium photocathode. Okay, so we've got it set up so that the wavelength of these photons is not producing a photoelectric effect. And of course what I can do famously is crank up the intensity. I can crank this right up, which means the number of photons. Look how many photons now are hitting that sodium. It's a lot of energy, a lot of total energy, but individually each photon does not have enough energy to eject an electron. So it doesn't matter how bright this light is, or how intense this light is, or how many photons there are, the photon density, it doesn't matter. I'm not going to see any photoelectric effect, and that's evident by the 0 ammeter reading. So let's just turn that down a little bit. Of course, to get the ammeter reading, I need to increase the energy of each individual photon, which means I'm going to start cranking this up into the green. And now you can see that these photons, the green light, each individual photon of green is able to eject an electron. So now I have the photoelectric effect happening. The question is asking me, what effect does this intensity have? In other words, what effect does cranking up the photon density have in regards to the kinetic energy of each individual photon, each individual electron? Well, we'll talk a little bit in a minute about the energy statement that you would be writing to do a photoelectric effect analysis, but we can just visualize this qualitatively. Take a look at the speed of these photoelectrons. They're just moving along at a relatively slow speed. If I increase the energy of each individual photon, then hopefully you can see that that's going to increase the speed of these. It's going to give it more, each individual electron will have more energy. So if I crank this up into the blues, you can start seeing these photoelectrons are now overtaking the ones from the green light. Okay, so we'll come back down to green. That's not what the question is asking. The question is asking what the relationship is between the this speed, this kinetic energy of each electron, and the number of photons, or the photon density. So let's go ahead and play around with this photon density dial, and what we're looking for is a comparison, a qualitative comparison of the speed with which these blue dots, these photoelectrons, are moving. Okay, so I'm cranking up the photon intensity, or the number of photons. So you can see that there's more photons hitting the sodium, which means there are more electrons, which means my ammeter is going to go up. The question is, what's happened to the speed? Well, hopefully you can see the speed has stayed the same. Look, you can really clearly see that here. There's no change in the speed, and that's really important. So there's no change in the speed, which starts making me think that probably A is the correct answer. As I increase the intensity, in other words, the number of photons, as the number of photons goes up, there's no change in this kinetic energy. Of course, we could also think about our energy statement. Whenever we do photoelectric effect, we're going to think about this. The sum of the energy initial is going to be equal to the sum of the energy final. And of course, the energy coming in from this is going to be the energy of the incident photon. So the energy of the photon, that's the only energy coming in. Now with the photoelectric effect, this energy coming in has to overcome the work function. And since we are seeing the photoelectric effect happening, it tells us this at this point. Photoelectric effect is observed. Since we're seeing that, then we also have, oops, I've used the wrong color. We also have the energy of the photoelectron. So I'm going to put that in, energy of the electron. And that's going to be a kinetic energy. So we're going to start writing our statement like this. We talk about HF, or it could be HC over lambda. We're going to say HF, the incident photon, is equal to the work function, and the work function is typically called HF naught, plus the kinetic energy, I'm going to call it EK, of the electron. And if we keep simplifying this down, we'll go HF incident is equal to HF naught, plus, of course, kinetic energy is half m velocity of the electron squared. And you can see there is nowhere in this equation is there number of electrons or intensity of electrons, photons, number of photons or intensity of photons. It's just not in the equation. And that's because when we do our photoelectric effect simple equation like this, we're really talking about one photon in and one electron out. We're only really considering this relationship. Now, this isn't strictly what happens if we take more precise measurements of the photoelectric effect, we do see some differences here. We don't tend to get exactly one photon to one electron, but this is a very good approximation, and it serves us very well in Physics 30. So for the most part, this is our assumption, and that means we can use this, this energy statement, and that means that we can say that this is the correct answer.